The technology of long-read sequencing now offers different alternatives to solve genome assembly problems, which cannot be resolved adequately by short-read sequencing. Here we present a hybrid approach allowing the sequencing and assembly of microbial and small eukaryotic genome using the MinION. Genoscope is a French sequencing center created in 1997. The Genoscope provides high-throughput sequencing data to the academic community. It mainly focuses on biodiversity involving de novo sequencing and metagenomic projects. As member of the MAP, we received 5 MinION devices last year in June. We performed our first run in June 2014 and have already performed about 30 runs. We sequenced well-known bacteria like Acinetobacter bailey and Escherichia coli, as well as wheat back clones. Our best run produced more than 250 megabases, with an average read length of 12 kilobases. These first results show a throughput heterogeneity. As reported by a large majority of MARC participants, the last chemistry showed several improvements. The yield and the proportion of 2D data are higher and reads are more accurate. As shown in the graph, we obtained several runs with 70% of 2D bases, and the average identity percent of 2D reads is now around 80%. We compare two different sharing size, 8 and 20 kilobases. The average size is 2 orders of magnitude higher when using the 20 kilobases library, suggesting that we obtain longer MinION reads when shared size increased. There is a real interest in prokaryotic genome to span RNA clusters. We observed the low mappability on the reference genome, and the mean identity to the reference of 1D reads was 56%, while 2D reads reveal a mean identity of 75%. The assembly of this read is challenging, as existing assemblers are not implemented to deal with long reads exhibiting a higher rate. We introduced NaS, a hybrid approach developed to take advantage of data generating using the MinION. The NaS workflow overcomes the limitation of existing assemblers. It enables the production of perfect reads and perfect genome assembly in only 3 days by combining sequencing data from 2 desktop sequencers, the MinION and the Illumina MySeq. Compared to existing methods, NaS is based on microassemblies. Illumina reads are first aligned on MinION reads. Fast mode is based on BLAT aligner, whereas sensitive mode is based on last aligner. These aligned reads are called seed reads. In a second step, we retrieve reads using a camera approach. We recruited reads that share at least 3 cameras with a seed read. In repeated regions, the microassembly leads to a complex quantigraph structure. In fact, in the second step of the process, a small fraction of reads that did not come from the correct genomic regions were recruited. These bad recruit reads produce branch points in the quantic graph. We select a path in the graph that is consistent with quantic alignments on the input MinION reads. To validate our approach, we use 6 MinION runs from Acinetobacter. We apply the NaS workflow to the MinION reads, and it generates near 30,000 reads with an N50 size of 30 kilobases. Here we compare the MinION and NaS read quality. This plot shows the alignment identity and the alignment size of the MinION 1D and 2D reads, as well as NaS reads. 95% of the NaS reads align completely with the reference genome with no error, and with an average identity of 99.99%. In contrast with correction-based methods, 66% of NaS reads are longer than their corresponding 2D MinION templates, owing to recruitment of reads outside the border of the template. In this case, the NaS reads are on average 1,850 base pairs longer than their corresponding 2D MinION template. By sampling randomly the Illumina dataset, we generate subsets of different genome coverage. Furthermore, we trim reads to obtain subsets with a different read length. Interestingly, we found that NaS reads are of high quality even with an ultra-low coverage. Additional coverage may be used to generate longer reads, but the method reaches a plateau rapidly. Using NaS on Acinetobacter, we were able to obtain a perfect read of 91 kb. The figures show a genomic region from Acinetobacter. The first track contains a 91 kb read alignment, green box, and purple boxes represent coding frames. This perfect read covers 80 genes. It validates the potential of the Oxford Nanopore technology as well as the performance of NaS. To demonstrate the utility of the NaS workflow, we attempt an assembly using a random subset of 30x of NaS reads. The resulting assembly is composed of a single config. When compared to an Illumina-only assembly of the Acinetobacter bailey genome, we observe a higher continuity, a higher coverage of the reference genome, and a better accuracy. The genome of Acinetobacter harbors 7 rDNA clusters, 4 of which are identical. NaS reads span completely the 7 rDNA clusters and include neighbor sequences that can anchor reads to its true location. As shown on the figure, also the Illumina-only assembly harbors a high continuity and a good completion. No contigs are found that span a rDNA cluster. We use 2D reads of 4 MinION runs from E. coli. We apply the NaS workflow and it generated near 22,000 reads, with an N50 size of 11 kb. To inspect the quality of the NaS read, they were aligned to the reference genome, and 92% of the reads aligned completely with the reference and with no error. Again, we perform an assembly using a randomly selected subset of 30x of NaS reads. The resulting assembly is composed of a single contig, and is similar to the one obtained using the PacBio sequencing platform. Our assembly contains less misassemblies but more mismatches and indels. The real novelty is to give access to these accurate genome assemblies through desktop and portable sequencers. Finally, NaS is an efficient method to generate perfect genome assemblies using desktop sequencers and based on microassemblies approach. NaS is freely available and can be applied to all kinds of long and inaccurate reads. The limitation of our method is currently the throughput of the MinION. However, if a higher throughput of the Oxford Nanopore technology becomes available, it may be speculated that NaS would provide an efficient method for sequencing organisms with large and repetitive genomes. We would like to thank people from Genoscope. This work was supported by the Genoscope, the CEA, and France Genomics. We acknowledge Nick Lohmann for availability of the Escherichia coli dataset. Moreover, we are grateful to Oxford Nanopore team.